Well, welcome everybody. It's really awesome to have you all here with us on this Tuesday afternoon. We are continuing with our revision program, and I'm going from paper 1 to paper 2 to paper 1 to paper 2 to paper 1 to paper 2. So today is a paper 2 day again. So we're going to have a look at some identities and general solutions, because these are often things that we get stuck on and struggle with and maybe leave out. And hopefully if we go over this level, then you and everybody else won't want to leave this out, and it's something that you'll feel confident to be able to try and tackle. Okay, so let's go and have a look at our very first question. By the way, before I get started, in addition to the formulae that we need to know for matric, so these are our compound angle formulae and our double angle formulae, we mustn't forget, now this is not on our information sheets, but we mustn't forget about our grade 11 formulae, our grade 11 identities. So just very quickly, I just want to talk about that as well. So I'm just going to write that here for us. So the first identity that we learn about in grade 11 is our tan identity. So we say that tan theta is equal to sine theta over cos theta. And this applies to tan theta in all shapes and forms. So what I mean by that is, if they give us tan squared theta, we would write this as sine squared theta over cos squared theta. If they gave us tan 2 theta, we would write this as sine 2 theta over cos 2 theta. If they gave us something weird like tan, I don't know, 90 minus theta, for example, we would write that as sine 90 minus theta over cos 90 minus theta. Okay, so that's the first one. They will expect us to use the tan identity, so please make sure that you've learned that. And then the second one that they would expect us to know is our square identity. So that is this. So sine squared theta plus cos squared. Let's just see if we can scooch over a little bit here. Sorry, I'm going off the screen. Sine squared theta plus cos squared theta is equal to 1. And then remember, we can manipulate this a little bit further as well. So what we could do is we could make sine squared theta the subject to the formula, and then it would become 1 minus cos squared theta. And then if they needed us to, we wouldn't be applicable in all situations, we could factorize what was on the right hand side here as well. So because it's difference of 2 squares, so it would factorize to 1 minus cos theta times 1 plus cos theta. Okay, and then we can do the same thing. We can make cos squared theta the subject to the formula. It would be 1 minus sine squared theta. And again, we could factorize that if we needed to. Okay, not always going to do that, but that is what's possible. Okay, so just remember, you cannot cancel over plus and minus signs. So if they want you to simplify, as you would be doing in an identity, you need to be able to factorize. Okay, but we'll talk about some other skills that we need when we have a look at this example. Okay, so the first one that they give us, that they want us to prove, is 1 over cos theta minus cos theta over 1 plus sine theta is equal to tan theta. So if you recall matrix, when we prove an identity, you are not solving an equation. So you cannot do the same thing to one side and do the same thing to the other side. Okay, that's not allowed. What we're essentially trying to do is simplify the left-hand side and get it to a trigonometric expression. Then we want to do the same thing on the other side, simplify it and get it to a trigonometric expression and show that these two are equal to one another. Okay, so you're not going to have an equal sign all the way down in the middle. you're going to separate the left-hand side and the right-hand side. So let's begin by looking at the left-hand side in the case of 5.3. So they give us 1 over cos theta minus, and then in the numerator, we've got cos theta over 1 plus sine theta. So essentially what we've got here are two fractions which we are subtracting. So let's think about what we would do when we had normal fractions, because the same rules apply. So let's pretend I had a fraction like 2, maybe let's make it a little bit bigger. Let's make it 4 over 5, and I needed to subtract 1 over 3. What would I do to my 5 and my 3? What would I do, Matrix? What do I need if I want to subtract fractions from one another? Exactly. Well done, Nhlanhla. Thank you, Cheslin. Quite right, Intercausa. I need a lowest common denominator. Yes, Kalipa. I need to make the denominators the same. I need a lowest common denominator. So I would look at my two denominators and I would say, in this case, okay, my lowest common denominator is going to be the product of 5 and 3. So my lowest common denominator is going to be 15. And then what I would do is I'd say, okay, I need to times this by 3. And what I do to the denominator, I do to the numerator. So I've got 15 at the bottom. That means I would have 12 at the top. And I would do the same thing on the other side as well. I would look at the 3, I'd multiply that by 5. What I do to the denominator, I've got to do to the numerator, and I would have 5 in the numerator over there. And now that my denominators are the same, now I can say numerator minus numerator and then keep the denominator. It's exactly the same process when you are working with identities. Okay, it's just not as simple, but it's exactly the same process. So you're going to look at the denominators, we're going to multiply them together like we multiplied 5 and 3, and in this case we're going to end up with cos theta multiplied by 1 plus sine theta. And again, I'm going to multiply the denominator here by my bracket, 1 plus sine theta. So I've got to do the same at the top over there. I've got to multiply it by 1 plus sine theta. Sorry, I'm just squashing it in a little bit. And then on this side over here, let's get a bit of color. I'm going to multiply that by cos theta. So I would have to do the same at the top over there. I would have to multiply that by cos theta. So I'm going to have 1 multiplied by 1 plus sine theta minus cos theta, and I'm multiplying that with cos theta. Is everybody okay on that step? Does that make sense to everyone? All good. Okay, good, good, good. So we're going to have 1 plus sine theta over here, because 1 into the bracket is not going to change either of those two, minus cos squared theta. And at the bottom, we've got cos theta into 1 plus sine theta. So now we appear to be stuck. And I use the word stuck in inverted commas because, of course, we're not really stuck. There is something that we need to do, but we are not allowed to cancel. So I cannot cancel the 1 at the top with the 1 at the bottom. I cannot cancel the sine theta at the top with the sine theta at the bottom. I cannot cancel the cos squared theta at the top with the cos theta at the bottom because of the pluses and minuses. All right, so at this stage, I either need to use an identity or I need to factorize. I've got to do something, right? But I'm not allowed to cancel. So just very briefly here on the side, if I've got 2 plus 5 over 3 plus 5, the reason I cannot cancel my terms is because it doesn't give me the same answer. If I cancel 5 and 5 like that, which is incorrect, I'm saying that this fraction is equal to 2 over 3, which it isn't. If I don't cancel and I work it out a different way, I'm going to end up with 2 plus 5 is 7 over 3 plus 5 is 8. And 7 over 8 and 2 over 3 are not equivalent fractions. Okay, so we are not allowed to cancel terms. You can only cancel factors. And that's why we have to factorize. Okay, so what are our ideas? Because we've already got factors at the bottom. We've got the cos theta multiplied by 1 plus sine theta. At the top, the numerator is the problem here because that's where our terms are. So what are the ideas, guys? What can we do at the top? Is there an identity that we can apply before we factorize? Okay, so Lebegang says we can use cos squared theta as 1 minus sine squared theta. I agree, we can do that. Is there anything else that we can do here? There's two things. You've named the one, and that's quite right, what you've suggested. Is there anything else we can do? It's going to give us the same answer as Lebegang suggesting. It's just a different way of thinking about things. Any ideas? There we go, Nhlanhla. Well done. Absolutely. Or we could work with the one. Quite right. So either we can change the cos squared theta into 1 minus sine squared theta, like Lebegang suggested, or we can work with the 1 and we can change the 1 into cos squared theta plus sine squared theta. We'll actually get the same result with either which one we choose to use in this case. All right, so either suggestion is absolutely fine. Lebegang, since you said that first, let's go with what you've suggested. 1 plus sine theta minus, and then because we are substituting a binomial, I've got to remember to put it in brackets. Okay, so 1 minus sine squared theta over cos theta times 1 plus sine theta. And now I'm going to remove those brackets at the top. So that's going to give us 1 plus sine theta minus 1 plus sine squared theta. And all of this is over cos theta times 1 plus sine theta. So now in my numerator, I have the 1 is going to cancel. 1 minus 1 is gone. So I've got sine squared theta plus sine theta. At the bottom, I've got cos theta into 1 plus sine theta. And again, I still cannot cancel over plus and minus signs. That sine squared theta plus sine theta is an indication to me that I need to factorize. Okay, so what sort of factorizing can I do in the numerator now? What kind of factorizing can I do? That's it, Nhlanhla. All right, take out a common factor, quite right. So I'm going to take out sine theta. That's going to give me sine theta plus 1 over cos theta. 1 plus sine theta. And of course, if I've got sine theta plus 1 or 1 plus sine theta, both terms are positive, so their order does not matter. Okay, not that the order of terms ever matters, but both of them are positive, so I don't even need to worry about taking out a negative. Now I can cancel my factors. Okay, and I end up with sine theta over cos theta, and of course, sine theta over cos theta is tan theta, and therefore it is equal to the right-hand side of my equation. Okay, so I have proved my identity. Is everybody happy with that? Are there any questions? Gugu's happy, cool. And Ntokozo Lebegang. great. Good, Mamelo. Good, Awami. Everybody's happy. Okay, brilliant. Okay, so that's just getting us into the swing of things. Thank you, Emihle. Thank you, Nondemiso. Thank you, Blessing. All right, cool beans. So in Trig, they will always give us marks for applying an identity. They would have also given us a mark for our lowest common denominator and accuracy on our numerator. Then for applying our identity, how many marks is that? 3. Has to be a mark on factorizing. 4, 1, 2, 3, 4. Obviously, there's not a mark on the answer. So here, I think there would probably be a mark for arriving at sine theta over cos theta. Okay, all right. If we're all happy with that, let's go and have a look at the general solution. This is a big one. Okay, we'll get rid of that and then we'll just write here next to it. Let's just clear some space. Okay, cool. All right, so now they want us to determine the general solution of 3 sine x equals 2 tan x. Okay, so now we're doing a general solution. We're not doing an identity, we're doing a general solution. So we are going to have an equal sign all the way down the center, and whatever I do to one side, I'm going to do to the other side. Okay, remember when I find a general solution, I'm basically finding a solution to an equation and it has to have multiples of either 360 or 180, depending on whether I'm doing a solution for sine theta or for tan theta. And it's going to allow me to find solutions anywhere on the Cartesian plane. All right, they haven't given us a domain to work in here, so they just want the general solution. Okay. Any ideas as to where we would start with something like this? What can I apply? There's an identity that I can apply here. What do you think we should do? How would you guys begin? That's it. Okay, so change tan theta. That's it. Use my tan identity. So I'm going to go 3 sine x equals 2 sine x over cos x. And remember, the 2 is only at the top because it means 2 over 1. Okay, good, lovely. And now after here, what would you do? What would we do in our next step, do you think? There we go. That's it. Good. Nhlanhla, Mamelo, that's it. Multiply by cos theta on both sides. Lovely. Or cross multiply. It would give me the same idea. Okay, so if I cross multiply or multiply by cos x on both sides, it means I end up with 3 sine x cos x equals 2 sine x, like so. Now what do we think we should do? So good, we've applied an identity, we've cross multiplied or multiplied by cos x on both sides, so we no longer have a denominator. Now what should we do? Okay, if I divide by, I'm not allowed to divide by sine x. So Johnny, I'm very glad that you made that suggestion, right? I'm never ever allowed to divide by sine x, okay? Because dividing by sine x is not an identity. I'm allowed to divide sine x by cos x. because that gives me tan x, that's an identity, but I'm not allowed to divide by sine x. So the idea is like this, okay? Imagine you were solving for a normal equation, not a trig equation, and you had something like this. X squared plus 2x equals 0, or better yet, x squared equals 2x. Let's say you had that. Would you divide by x on both sides? So if we're looking at the blue, would I divide by x on both sides? Can I do that? No, I can't do that. I'm not allowed to do that because then I lose a solution, don't I? And what if one of my solutions was 0? Then I'd be dividing by 0 and it would be undefined. So the idea is that because it's quadratic, I would move this over to the other side, make it equal to 0, and then I would factorize, wouldn't I? Okay, so it's the same idea over here. I'm not allowed to divide by sine x. Number one, it's not an identity. Number two, I would lose a solution. So in the same way that I would move the 2x over to the other side and then factorize out a highest common factor, I would do exactly the same with what I have here in orange. I'm going to move this 2 sine x over to the other side. So I'm going to end up with 3 sine x cos x minus 2 sine x equals 0. And now what can I do? So like I took out the x here on the right-hand side in the blue as a highest common factor. So I can't subtract unlike terms, Kalipa, just like I can't say x squared minus 2x. So I would take out, that's it, Gugu, that's it, Mamelo. I would take out sine x as a highest common factor. So I'm taking sine x out. That leaves me with 3 cos x minus 2 equals 0. Everybody happy with that? Okay, so I've taken sine x out as a highest common factor. I can't take out cos x because I don't have cos x in both terms, but I do have sine x in both terms. That's why I can take sine x out. Okay, so now I have either sine x equals 0 or cos x is going to be equal to 2 over 3. Does that make sense to everyone? Are we all good so far? Okay, good. All right. So now we're at the point where we can start finding our reference angle or our key angle or our PAA, depending on what it is your teachers taught you at school. And thereafter, we can decide which quadrants we're working in and go about getting our general solutions. Okay, so what we're going to do is work with sine x equals 0 first. What would our key angle, reference angle, or PAA be if sine x equals 0? What's our PAA? You'd need your calculators, or maybe you know it off by heart already. Good, well done. So that would be 0 degrees. Okay, then we would look at our ratio, which in this case is 0. And under these conditions, as under a few conditions in mathematics, we would consider 0 to be positive. So that means thinking about our cast diagram, we would be either working in quadrant number 1 or quadrant number 2. Okay, so Johnny, on the calculator, you've got to go, because you want to calculate an angle. So you're going to go shift sign, and then you're going to put in the 0. Okay, and then it's going to give you 0 degrees. Okay, so shift sign. So in quadrant number 1, our angle X, no problem, would be equal to 0 degrees. We don't have to write the 0 degrees, incidentally, when your PAA is 0 degrees, but I'm just putting it in anyway, plus K times 360. K is an element of the integers. So that would be our general solution arising from the first quadrant. Then I know that there is a second quadrant where sine x is also positive. That's the second quadrant. So here I would use my reduction formula for the second quadrant, which should be 180 minus 0 degrees plus k times 360. K is an element of the integers, so it would simply be x equals 180 plus k times 360. K is an element of the integers, like so. Sure, okay. Amahle, I'm sorry, it's kind of, there's the beginning part. So 3 sine x equals 2 tan x. And then I'm just going to scroll down again. Okay, Amahle. Anybody else who wants to take a screenshot, go for it. Okay, going down again. All right, and I'm using k times 360. Why? Why am I using k times 360? No problem, Amahle. So I'm using k times 360 because the sine graph repeats itself every 360 degrees. Quite right. That's the period of the sine graph. Thank you so much, Gugu. Perfect. Okay, yes, it's the period of the sine graph. Quite right. Okay, so now let's consider cos x equals 2 over 3. So again, Johnny, if I want to find my PAA, I would have to go shift cos and put in the 2 over 3. What do we get as an answer? What's our reference angle, key angle, PAA? Quite right, we would get 48,19 degrees. Okay, good. Well done, everybody. That's perfect. And now again, I am looking at my ratio. All right, I can see that it is positive. So again, when I think about my cost diagram, whoopsie, putting it in the wrong place. Cost diagram over there. Again, there are two quadrants where cos theta is positive. The first quadrant and the fourth quadrant. So those are the quadrants, good, first and fourth, in which I need to work. All right, so here I'm going to say x is equal to 48,19 plus k times 360. That is for quadrant number 1. Nothing else that I can do there. Or in quadrant number 4, x would be equal to 360 minus, because that's the reduction formula for the fourth quadrant, minus 48,19 plus k times 360. K is an element of the integers. So my final solution is 311,81 plus k times 360. K is an element of the integers. All right, and there we go. We are finished with this question. They asked us to find a general solution, and so we did. All right, are there any questions about what I have done here? Mamelo's happy, Gugu's happy. Cool. Ntokozo, thank you. Cool, immediately. All right, so just very quickly, Kalipa, your teacher may have called it something else, Kalipa. It's your reference angle, your RA, or your key angle. Sometimes teachers don't refer to it. I call it a PAA for positive acute angle, but maybe your teachers called it something different. Does that make more sense now? Key angle or a reference angle instead of PAA? And Johnny, the reason that it's 360 is again because of your period of your cos graph. Okay, so if cos x is equal to 2/3, your cos graph repeats itself every 360 degrees. That's where we're going, plus k times 360. Neo, you actually don't. I think you'll find that most teachers would do that. Oh, good, Johnny. But you don't need to have it on every line, but you do need to have it at least once. But I think those of us that are teachers, we just kind of get into the habit of putting it on every single line. Okay, but yeah, it has to be there at least once. Okay. Yeah, k is an element of the integers. Cool. Cheslin, you might be using a different rule. There's a different rule that you can use for cos theta. So you can do that. It will give you the same answer. I just prefer to do it in quadrants. I think this is the way that most people do it. But you can do it that way if you want to. Theoretically speaking, though, your reference angle is always supposed to be positive. All right. Nhlanhla, you said, what if it was minus 2/3? So Nhlanhla, your PAA would still be the same. It would still be 48,19. What would be different is that you would work in quadrants 2 and 3. So your first general solution would be x equals 180 minus 48,19 plus k times 360. And your second general solution would come from x equals 180 plus 48,19 plus k times 360. So you'd be working in quadrants 2 and 3 as opposed to 1 and 4. Exactly, Cheslin. All right. So it's the sign of your ratio that's important. The value of your ratio you use to calculate the value of your PAA, but it's the sign of your ratio, whether it's positive or negative, that determines in which quadrants you're going to work. Okay, so the idea is this, and again, if you're always thinking about the graphs, then it makes life easier. So I'm just going to do this for cos x, but essentially what you're doing, when you say cos x equals 2/3, you are working with a cos graph. So, okay, that's a very skew, horrible set of axes, but if I quickly just sketch a cos graph over here, that would be 90. Our minimum here would be at 180. That would be another x-intercept at 270. And then we'd have our maximum over there, 360. So if this is 1, because this is the graph y equals cos x. So this y value over here is essentially that value over there. It's the same thing. It's your output. Okay, so 2/3, 2/3, would be somewhere over here. So if I go across where y is equal to 2/3, there is my solution in the first quadrant. So in other words, this 48,19. And then here is my solution in the fourth quadrant, the second one over there. Yes, William. You're
Hi, ma'am.
welcome. Hi, William.
Ma'am, I just wanted to ask,
Mm.
if I did my question this way, where after using the tan identity and
Mm-hmm.
after dividing it all or cross multiplying and
Mm-hmm.
then transposing to the left, ma'am, what I
Yes.
did was I took out cos x as my common factor. And that's then I got cos x equals 0 or sine x equals 0. And I
Okay, now,
used
okay, so now the problem with that though, William, is that cos x is not a common factor. So if I go back and I highlight cos x, can you see it is only in the first term? I do not have a cos x in the second term. So your second term is the one that I am putting a pink circle around. Your first term, I'm going to put a blue circle around, because remember, terms are separated by pluses and minuses. So you can't take cos x out of the pink circle because there isn't a cos x there for you to take.
yes, ma'am.
Okay, so that would be the issue. That would be the issue with it. If they had a cos squared x or a cos, or mind, then it would be like terms. But if they had, let's say they had a cos squared x in that pink circle, then you can take cos x out as a highest common factor. But it was only sine x that was the common factor, so there would not be another way to factorize that, unfortunately. Sorry, William.
Thank you.
Okay, no problem. Does that make sense to you? Happy with that?
Yes, ma'am.
All right, cool. Okay, well, if everybody's happy, let's go and have a look at something else. Okay. Oh, by the way, this was out of 6. So let's just quickly go through where our marks would be allocated here. So there would definitely be a mark on an identity. There always is. I'm sure there would be a mark on the factors. Do not leave off the equal 0 when you are factorizing. Don't do it in paper 1. Don't do it in paper 2. Often in matric, there is an accuracy mark on that line. So if you leave off the equals 0, they will penalize you for that. So what's that? 2 marks. Okay. Maybe they would have allocated a 3rd mark there, but I'm not 100% sure about that. There's definitely going to be a mark on the correct quadrants. And then on your general solutions, 1, 2, 3, 4, 5. Okay, so maybe not a mark over here, and then quadrants and general solutions. Okay, on that side over there. All right, let's go down and go and have a look at another identity. Okie dokes. So they want us to prove the identity sine theta minus tan theta times cos squared theta over cos theta minus 1 plus sine squared theta equals tan theta. Okay. So starting with the left-hand side again, let's get it down. We'd have sine theta minus tan theta times cos squared theta all over cos theta minus 1 plus sine squared theta. So quite a lot going on the left-hand side over here. What would you do in the numerator? Yes, Amahle.
Good evening, ma'am.
Good evening.
You would change the 1 plus sine squared theta, and you would. So first you'd have to change it, and you would change it to cos squared theta, because 1
Are you
plus.
talking about in the denominator?
Yes.
Okay. All right. Okay.
And then in the numerator, you'd have to change the tan theta into sine over cos theta.
Good. Well done. All right. So let's start with that. Thank you so much, Amahle. An important thing for you to do when you're working in a numerator, and now you've got another denominator and another numerator, like you'll have when you change tan theta, set it out in such a way that you can clearly see what's in the numerator and what's in the denominator. So what I mean is this, okay? You've got sine theta minus sine theta over cos theta. So now you can clearly see both sine thetas are in the numerator. It's the cos theta that's in the denominator. And then when I'm going to multiply by cos squared theta, I'm going to make sure that that is also in the numerator. Okay, and that's just going to help you see what you can cancel down and what you can't. Okay. It's important when you're working with fractions to know what's at the top and what's at the bottom. And so our setting out here is really important. Okay, so Amahle made a suggestion. She said, let's change the -1 plus sine squared theta into cos squared theta. So remember, she said into cos squared theta. So remember, cos squared theta is 1 minus sine squared theta. Okay, so if we have a look at what we've got here, can you see our signs are the wrong way around? Here, this is a positive, isn't it?
Yes.
Yes, but that one is a negative.
Negative.
Yes, and this one over here is negative, but this one over here is positive. So we can't say that this portion at the bottom, we can't say it's equal to cos squared theta because it isn't. All right. So there's going to be a little bit of manipulating that needs to go on down at the bottom. All right. What I think I would probably do, which because there are 3 terms in the denominator, is I think what I might do here, instead of trying to take out a negative, what might be easier is to do what Nhlanhla suggested in the very beginning when it came to this denominator over here. Do you guys remember Nhlanhla made the suggestion, with this numerator over here, Nhlanhla made the suggestion with our numerator that we could change the 1. So rather than changing the cos squared theta, Nhlanhla said, let's change the 1 into sine squared theta plus cos squared theta. I think that's just going to be a little bit easier for us in this case. So what I'm going to do is bring down the cos theta minus, and then in place of the 1, and now again, because the 1 is changing into a binomial, use brackets. Okay, so now I've got sine squared theta plus cos squared theta. And then I'm just going to extend that line a little bit, and then I'm going to bring down my plus sine squared theta like so. Is everybody happy with what I've done so far? So I've applied 2 identities, the tan identity at the top and my square identity down at the bottom. Are we all cool with that? All right, so now what I want to do is try and simplify things a little bit. Now remember, I cannot cancel over plus or minus signs, but I can cancel over multiplication and division. So I am allowed to say cos theta goes into itself once, and it goes into cos squared theta, cos theta times. That is allowed because I've got a times here, or at least I did before I started fiddling with it. Okay, I've got a times over there. So simplifying my numerator, I'm going to end up with sine theta minus sine theta times cos theta. Is everybody happy with what I've done here? Does that make sense? Yes, cool, okay. And now at the bottom, I'm going to remove these brackets and I'm going to end up with, yes, okay, good, thank you. I'm going to end up with cos theta minus sine squared theta minus cos squared theta plus sine squared theta. Okay, so bringing down my numerator now, I've got sine theta minus sine theta cos theta. And at the bottom, the minus sine squared theta and the plus sine squared theta are going to add up to 0. Okay, so these terms over here, this one that I'm putting the yellow circle around, and this one that I'm putting the yellow circle around, they are going to end up adding up to 0. So this is going to give us cos theta minus cos squared theta. So now what I'm going to do is, let's just go up a little bit. I'm going to come and write up here. Okay, obviously you guys will be writing one line under the other. I'm just going to do that so that we've got it all on the screen in front of us. Okay, so what am I going to do? I can't cancel over plus and minus signs. So what can I take out in the numerator? So let's do that first. What can I take out in the numerator? I can take out sine theta. Good, well done. Because remember, I've got sine theta in both terms. Remember, terms are separated by pluses and minuses. So in the numerator, I'm going to take out sine theta. That's going to leave me with 1 minus cos theta in the brackets. That's it. Well done. At the denominator, or in the denominator, what am I going to take out? That's it. Good. Well done, everybody. I'm going to take out cos theta. Excellent. And that's going to leave me with 1 minus cos theta in brackets. There we go. And now that you have factorized, because you cannot cancel over plus and minus signs. When you see plus and minus signs, it's an indication to you that you have to factorize. You can only cancel factors. Okay, so I can cancel the factor 1 minus cos theta at the top with the factor 1 minus cos theta at the bottom. All right, and then this leaves me with sine theta over cos theta. And again, I'm happy and smiling because I know that sine theta over cos theta is tan theta, and that's what they gave me on the right-hand side. Okay, how are we feeling? Is that okay? Is that making sense to everybody? Are we all good? Any questions? You sure there are no questions, guys? Okay. All right. So I'm just having a look at our time, just seeing how much time we've got left. What I'd like to do, and I just don't want to run out of time here, is this general solution with you. I think we should be able to fit it in the time that we've got. Yolanda, if you have to jump over, then maybe we need to do that, but let's just wait and see what happens.
No problem.
Okay, all right. So in this general solution, we've got sine x minus 30 equals cos 2x. So what's important about this general solution is that we've got sine x, or sine x minus 30 on the one side, but we've got cos 2x on the other side. Okay, so what do we think we should do in this case? If we've got the sine of one angle on the other side and the cos of an angle on the other side, what do we do? Why are we not allowed to divide sine x by cos x? I'm glad you said that, Gugu. Why is that not allowed in this case? In this case, why is it not allowed? It's not allowed because the angles are different. The angles are different. Yes. Okay, if it was cos x minus 30, then we're allowed to do that. Okay, but because it's not, okay, the angles are different, we are not allowed to do that. Okay, so I'm glad we're doing this example because this is something that we often don't think about when we are working. All right. So yes, William, I understand why you are thinking that this is going to be a compound angle. But if we expand it according to our compound angle formulae, we're going to end up with something that's going to be quite long and probably a little bit difficult to work with. Okay. If they give you a general solution and it's sine x on the one side and the cos of a different angle on the other side, use co-functions. Okay, so in other words, what I'm saying to you is remember sine x is equal to cos 90 minus x. Do you remember that? All right. So the best thing for you to do here, right, is to use co-functions. So we will do as follows, right? So we're going to leave it as sine x minus 30 on this side. And on the other side, we are going to rewrite this as sine 90 minus 2x. Is everybody happy with that? Or do I need to explain that a little bit? You sure? Okay. All right. So Gugu, just very quickly, I don't know if we'll be able to finish it. Yes, Amahle, so you've got a hand up?
Ma'am, can it not happen
Yes.
vice versa? By
Yes,
changing...
absolutely. Absolutely.
Okay.
So you could do it on either side. It wouldn't matter.
Okay.
It's not a problem. Oh, gosh, that's a terrible right angle triangle. Yes, Amahle, you could do it on either side. It really doesn't matter. Okay. So there's
Okay,
my
thank you.
90-degree angle. If I decide that this angle over here is called 2x, and I call this side A and that side B and that side C, okay? Just to explain the right-hand side, if I talk about the cos of 2x, remember the cos of any angle is adjacent over hypotenuse. So that would be the ratio B over C, okay? Now, if I talk about, if I consider this angle over here, so this angle here, that one over there, that would be 90 minus 2x, wouldn't it? Because of the angles of a triangle. So if I talk about the sine of 90 minus 2x, so now I've changed my reference angle, I'm now talking about that angle over here. If I talk about the sine of that angle, it would be equal to opposite over hypotenuse. It would still be B over C. Okay, Gugu. Okay, Neo, does that make sense to you? Do you remember that? All right. Cool. And then what we see on the right-hand side, this is positive. So what I like to do is this. I like to work with this bit over here on the left as my angle. And now again, I'm working in the cast. We're working with the cast diagram. And I'm saying there are two quadrants in which sine x is positive. Quadrant 1 and quadrant 2. So my angle in this case, matrix, is x minus 30. In quadrant number 1, it's going to be equal to my PAA. So I'm going to use 90 minus 2x as my PAA plus k times 360. K is an element of the integers. Okay, and then I'm going to take my 2x over to the other side. So that would give me 3x. I'm going to take my 30 over to this side over here. That's going to leave me with 120 plus k times 360. K is an element of the integers. And dividing through by 3, I'd get x equals 60 plus k times 120. K is an element of the integers. Are we happy with that? Okay, so Kalipa, I transposed. I took the minus 2x over to the other side. All right, but I'm not finished because I need to do a solution in the second quadrant as well. So here I would end up with x minus, where am I writing? With x minus 30 is equal to 180 minus 90 minus 2x plus k times 360. K is an element of the integers. Okay, and again, what I would need to do here, let's just, oopsie, let's just get rid of those, is remove my brackets. Minus 90 plus 2x, so just be careful when removing brackets. If you've got a minus in front, you have to change the signs of the terms inside. And now I can go ahead and collect like terms on either side. Okay, so here I would end up with x minus 2x. Here 180 minus 90 is 90. 90 plus 30 would leave me with 120 again. And then here I would need to simplify that, so I'd get negative x. And then divide through by -1. So x would be equal to negative 120. And then here it could be plus or minus k times 360. K is an element of the integers. Okay, Cheslin, did I make a mistake? Minus 90. No, okay. All right, so oh, did I make a mistake by the first general solution? Did I? Where was my mistake? Yolanda, can you see any mistakes? Have I done something wrong here?
Not yet. I'm still looking, but not yet.
Dividing by 3? Okay, so I divided 3x by 3 and got x, 120 by 3 and got 6. Oh, it must be 40. Oh, sorry. Silly me. Quite right. Thank you, Cheslin. Sorry. Quite right. This should be 40. There we go. That's better. Thank you.